experimentos mentais, thought experiments, are common in science and philosophy. And I hope you know, maybe you know about Galileo's falling bodies and Chinese room and Schrödinger's cat and trolleys and many, yeah? Thomson's violin. But in mathematics, thought experiments sounds different from science and philosophy. And some people think that it's just a façon de parler, it's just an unnecessary term in mathematics. Mathematics is about proofs, constructions, at least. And it's just, there is no need to use the word experiment. Experiment is when you have a contact with the reality of your body via your senses. And you don't have it in mathematics, they say. Or the opposite extreme is, people say, the whole mathematics is a thought experiment, since mathematics is a priori. Everything is a thought experiment in mathematics. And yeah, both make sense, but I disagree, and I think there are genuine mathematical thought experiments, and I will try to show you that it's so.
You have to go page down.
Page down.
Page down.
Okay. So, and as I said this, these are some of my publications, my recent publications devoted to thought experiment. For some time I was studying this problem, and in this work I showed that there are genuine thought experiments, and I gave a bunch of examples, so you can find them. Today I haven't had much time to present all of them, but in these publications you can find examples with pictures and explanations from various areas of mathematics. But in this talk today, I will focus a little bit on mathematical impossibilities. Why? Because when we take this idea that mathematics is a priori, we kind of have more problems with impossibilities and questions which are kind of open questions. And I think that mathematical thought experiments is an approach to impossibilities in mathematics, which can help resolving some of these problems. And finally, I will say that mathematics is not only deductive, but also can be experimental. So the plan is very simple, two parts. I will start with impossibilities in mathematics, and then I introduce mathematical thought experiments, and I will use proofs by contradiction as an example of impossibilities and how we can treat them via mathematical thought experiments. So the problem is that impossibilities are very important in mathematics. As for foundations, methodology, and also nowadays, because we are at the beginning of a huge project of automatization of mathematics, it's very important to deal with impossibilities because everything should be constructive. So the general question is, how is it possible to extract some mathematical knowledge from impossibilities, from something which doesn't exist? It's impossible. Right? And in particular, what could be the logical foundations for impossibilities in mathematics, and also what are the epistemic mechanisms of thought experiments which help us to deal with these impossibilities. The second question will be my focus for today. So, in mathematics, proving impossibility sometimes is more impossible than proving possibility. Lutz, a historian who has published a book on impossibilities, he is focusing on proofs of impossibilities, and he is saying that before, in mathematics, impossibilities were kind of underappreciated, and their importance was not so understood as today. So he's saying today, impossibilities results are among the most famous theorems in mathematics. However, we have seen that in earlier times, an impossibility result was often considered as a rather uninteresting lack of result, or such a second importance to a positive result. And he's saying that also that a problem has a different nature than an argument of impossibility. So even in our life, it's something different. Impossibility is really something different. But along with theorems about impossibility, there are various other impossibilities in mathematics. So what Lutz is talking about is that it is impossible to accomplish a particular task for some precisely specified means. However, there are other types of impossibilities. And the major aim is to overview and classify the variety of impossibilities in mathematics. And so here is some list with which I came up, and so far, probably incomplete, but as I think it's important. So the first one is some construction in Euclidean geometry which are impossible with ruler and compass. For example, trisecting angle or doubling a cube. Are there some mathematicians in the audience? No. It's good to know. Okay. Please stop me if you have questions. Well, the first one is exactly to prove that something is impossible. And the second is proof by contradiction, is another type, because in proof by contradiction we always assume something impossible. I will come up with some details in a minute. But in a proof by contradiction we assume not A and come to contradiction and prove that A, but not A is impossible. Number 3 in this list is other constructions which sometimes appear unintuitive for us, but mathematically they are fine, they are settled. For example, famous Banach-Tarski paradox is when you can take a ball and split it in 2 copies of itself. It's very, in fact, not just 2, but infinitely many copies of itself. It's really counterintuitive, but it's perfectly fine for mathematicians. The intuition, intuitively, it's impossible. It looks impossible for us. Then, it's relevant to mention number 4 is a type of impossibilities which are not yet regularized in mathematics. For example, at some point complex numbers were impossible, and it was impossible to find solutions of polynomials, particular polynomials, right? And there was a moment when people were solving such problems, but complex numbers were not existing yet. They were like impossible. And my example today will be about non-Euclidean geometry. Is another example of something which at the moment can be impossible, but it will become possible with some help of thought experiments. And finally, a very curious type of impossibility is, so I call it fictional impossible. I would appreciate if you suggest some other terminology. It's exactly when mathematicians are saying, oh, the graph is heavy, or Archimedes, he has heavy line segments when he solved a problem of parabola, or Lakatos in proof and refutation, he has stretching Rubbermaid polygons. There can be heavy graphs, and so it's exactly when mathematicians are mixing up physical properties and mathematical abstract objects. It sounds like fiction, and it can be even shaped as a short story, but these objects do not exist in mathematics. They don't have, mathematical objects do not have physical properties. So this is my list, and so far, which is incomplete, but the idea is we have to deal with this variety of impossibilities. We have to systematize it somehow and answer the questions, how is it possible? So I think that proving some impossibility means potential discovery of new possibilities sometimes. And now I will move to proof by contradiction. I will repeat a little bit what I said at the conference, but not everybody heard my talk. So it's just a little bit of overlap. Proof by contradiction is one of the examples of impossibility. The scheme goes like this: 1, 2, 3, 4. We imagine that we have to prove A. We assume not A, and we have to demonstrate that this assumption leads to a contradiction, right? And therefore, we conclude that A is true. Is it clear? Yeah, simple. But because of this premise that we assume something is possible, proof by contradictions are usually claimed weak and problematic proofs compared to direct proofs. Exactly because they are based on the wrong premise. Because it postulates the impossible state of affairs. So it may also cause some errors on the way to contradiction, and finally people say that the epistemic gain is insignificant in comparison to direct normal proof. So in sum, it's commitments to impossible, risk of accidental contradiction, and insignificant epistemic gain. So my thesis is that these disadvantages can be turned into advantages by means of thought experiments, by approach of thought experiments. So what are mathematical thought experiments. As I said, it's quite an interesting concept. So I define them as a method of reasoning towards the solution of a mathematical problem. They have a form of an experimental scenario which helps to representing a problem in a different perspective and eliciting our past experience, thereby linking the problem with external resources. Usually, thought experiments are undistinguished from other types of heuristics like reasoning with pictures or models or metaphors. However, I think they are a separate independent method. So the key properties of thought experiments are observation. They are based on observation and they involve sensory experience. So it's always something visual, usually visual. And they allow for properties and propositions which go beyond the given theory or given practice. For example, here is my picture. Okay. So here is a drawing of a graph. The first one is a canonical drawing of a graph. It's just like, that's how you have to draw a graph. You should draw a graph. That's how the textbook teach you drawing graphs. Maximally symmetrical, and the edges should be of the same length. Because there is no such a concept as the length of edges. Edges is this. These are vertices and these are edges. Yeah. But the thought experiment goes like this. Imagine that this is a bunch of oranges in a net, and you just pick up one of them, one of the oranges, and let the rest of it hang down. What would be the configuration of the oranges in the net? And it will be something like this, right? This little thought experiment, it's very simple, but it gives you an idea how you can redraw the graph. It's not very obvious how you can redraw the graph for solving some particular problems. In this second drawing, you can see immediately some properties of this graph which you can't see on the first one. For example, you can see that there are two antipodes of this graph. The antipodes are the most distant vertices in the graph. And also you can find the so-called diameter of the graph, the maximum distance between the antipodes. On the first drawing, it's very difficult to solve this problem. In the second, it's much easier. Well, this is my simple example. And you can see that you rely on observation. It's an experiment because you have to observe things. You don't go with axioms and rules of deduction to conclusion, right? So you're really doing your observation. But you have properties, physical properties, oranges and heaviness of oranges, the gravity is present, which are not a part of graph theory, which is not a part of mathematics. So in this sense, you are going beyond the practice of graph drawings and graph theory. That's why they are thought experiments. You have to use your imagination. But at the same time, you rely on your past experience of oranges. And it's a real experience. You did interact with the real life, with the real world, when you gained this experience. So why thought experiments could be applicable to such situations when we are dealing with impossibility? For example, proof by contradictions. The very form of them suggests this similarity. In proof by contradiction, we ask, what if A is not true? So I have a quotation from a real mathematician who is saying, for me, it's much easier to think about a proposition in terms of what if this wasn't true. That is usually my first instinct. This makes proof by contradiction the natural first choice. For instance, if I were asked to prove something like, prove that a non-singular matrix has a unique inverse. My first instinct would be, what if a non-singular matrix had two inverses and from then on the proof follows clean? So both proof by contradiction and thought experiments are specifically helpful when it is difficult or impossible to find a direct proof. Hardy described proof by contradiction as one of mathematicians' finest weapons. And well, why are they helpful in such cases? Exactly because, as I said, you can, by means of thought experiments, you can go beyond the given practice. You can link with resources beyond the given theory. But the difference of thought experiments with proof by contradiction, the huge difference is that this experience in thought experiments can be very broad. So it can be another part of mathematics, it can be geometry, physics, science, and it can be life experience, like the net of oranges. Finally, I move to the question how thought experiments can help us with problems of proof by contradiction. The first one is about impossible premise and the consequent commitments. So, because we are having this impossible premise, it confronts us with a paradox. On the one hand, we assume something impossible, which has no model in our theory, but on the other hand, we somehow construct it in our proof. In order to go to arrive to contradiction, we really construct this impossibility and see what happens. And what happens is a contradiction. So this paradox raises a question: how can we form a mathematical belief on the basis of something impossible? I think that the perspective of thought experiments can help to clarify this problem. So, of course, when we pursue the constructive way of mathematics, that everything has to be have to have a model and has to be constructed, then it's really difficult. This idea that thought experiment can be used by treating impossibilities, I found in Berto and Iago book when they are discussing the problem of metaphysical and epistemic commitments of impossibilities, because we have to solve these problems. We have to answer the questions: in which sense something is impossible, or senses, it can be many senses, and in which sense we believe, or do we have to believe, do we have these commitments to believe into possibilities and impossibilities in what way? So they say that both in proof by contradiction and in mathematics and thought experiments in science and philosophy, we are not committed to, we don't have these commitments, especially in thought experiments, because they have this situational character. Also Dorn, he has a paper devoted to these minimal commitments we have in thought experiments, saying that the situation-specific minimum commitments, instead of having metaphysical modality, is the advantage of thought experiments. So in other words, because of this situation-specific character, which of thought experiments, which determines the type of impossibilities involved in the scenario, and also the degree of engagement of the experimenter. We don't have these commitments, right? So we can just suppose something in a thought experiment, or we can conceive something, or we can really imagine it in an imagistic way, get involved in the thought experiment. It really depends on us and on the problem to be solved. But anyway, it's always a situation which comes into our imagination, and that's it. So this perspective somehow dilutes the commitments, epistemical and metaphysical commitments. So the second problem is, as I said, I call it accidental contradiction, is that because we reason from an impossible premise, anything can come up in the construction, and we cannot rely on intuition because it's something impossible. Our intuition may not help. So there is a huge risk that we can make mistakes in our calculations, and therefore the contradiction can come from mistakes. And this contradiction has nothing to do with the impossible premise. So we come up with an accidental contradiction, which is very unfortunate. The advice, the practical advice, is to isolate this impossible premise from all the rest of the proof. For example, on the way you can have some lemmas and you try to prove them independently on this premise. And then your proof becomes clearer and easier to check. Right? So, of course, this is reasonable to isolate the wrong premise. However, by doing so, you are actually enforcing your theory, the given theory. But alternatively, you can think about it as a potentially plausible assumption and try to see what happens. So instead of being in a mode of a proof, and follow the rules of a proof, that is, searching for contradiction, you can think of it as an experiment and try to observe what else can happen. Imagine that this premise is plausible. And this is where a thought experiment can help, because a thought experiment suggests a different strategy, namely thinking what else can happen, what conditions, under what conditions this premise can be false, or at least can be plausible. And then you can create another theory instead of enforcing the given theory. And in this case, an epistemic gain actually can be much bigger. Why? Because you are creating a new theory, which can be much richer, and it can be much upper level of generalization. And also you are connecting your theory with another external resources, therefore enriching it. Now I want to give you some examples, but I will start with a non-example. This is proposition 10 from book 3 of Elements of Euclid. So he's proving that two circles intersect in no more than 2 points. Right? And he's trying it from contradiction, so he asks, what if it is not so, and there are 4 crossing points? And then, as you see, he is committed to draw an impossible figure with 4 intersective points, H, B, G, and F, and 2 circles, one of which, of course, will be an oval or something like that. So here we are inside Euclidean geometry with a picture which is impossible for Euclidean geometry, and we are trying to prove a fact, a theorem in this theory. Right? But Euclid is just pretending that everything is fine with this picture, and I will not go through the proof, but it's quite easy to come up with some contradiction. So, in a sense, it is a kind of formalized version of a thought experiment. He kind of starts with a thought experiment with this premise. Imagine that it's not, it's more than 2 points, it's 4 points. But then the proof tells him, find a contradiction, that's it. And now I will give an example of a thought experiment. So there were many. The postulate 5 in Euclid's geometry is saying that given a straight line and a point outside this line, there exists a unique line parallel to the given line which goes through the point. So there is a line, there is a point, and we can draw only one parallel line to it. And there were many people trying to prove this postulate. and all of them failed. Lobachevsky was among them, and he tried from contradiction as well. So he said that imagine that it's impossible. Imagine that there may be more than one line parallel to the given line to draw through the point. Of course, this drawing is again impossible in Euclidean geometry. However, it makes sense in hyperbolic geometry, right? I have a drawing. Yeah, here you have a Russian word from Lobachevsky book, which means a picture, рисунок. But it's a very bad copy. So they are just lines without straight lines, right? This drawing from point R parallel to the given line A, and there are many of them possible. So the important difference with Euclid's non-example and Lobachevsky's thought experiment is that it extends the Euclidean practice. But the thought experiment tries to make sense of this premise that there are many lines drawn from this point. So Lobachevsky idea, let's try this thought experiment. Let's draw the picture. Yes, it looks like it's like a picture in the Euclidean geometry, but it doesn't make sense in Euclidean geometry. However, let's try find some conditions so that it would make sense. Let's observe how it's possible and create another theory, a non-Euclidean geometry. So this was, in a sense, an experiment because you have to observe the situation, but you are going beyond the practice. You are trying to find conditions so that this picture is possible. Right? And this is why it's a thought experiment, because you are going beyond the rules. So, Lobachevsky drawings is impossible in Euclidean geometry, but possible in non-Euclidean. Why? Because the fifth postulate is independent from Euclid's premises. But how to prove it? Not everybody managed to do this, and I believe that when you look at the problem through in the perspective of a thought experiment, it makes sense, and then you find some mathematical terms how to make it strictly acceptable in mathematics. So this is, as a mathematician said, the disadvantage of proof by contradiction is that the target is to obtain some contradiction. Usually there is no way of telling beforehand where it will come up. But this is in fact a change, but not a problem, as I see. What is contradiction? What if contradiction does not exist at all, as in Lobachevsky case? And so his strategy was to stop searching for a contradiction and try something else, making the premise plausible. So let me conclude. I departed from the view that mathematics is a priori and there are no genuine thought experiments in mathematics, or the whole mathematics is a thought experiment. But now the final picture can be reconstructed as the following. A significant part of mathematical reasoning is based by its nature on thought experiments. Their key features are observation, use of sensory experience, and extending the given practice. If we look at some problematic methods in mathematics, such as proof by contradictions, which involve impossibilities, in the context of thought experiments, they can be understood much better and better appreciated. And finally, I just want to recap the list of impossibilities in mathematics. So there are some constructions of Euclidean geometry, proof by contradiction, constructions which appear intuitively impossible, some irregular, not yet regularized impossibilities in mathematics, and fictional objects in metaphors and thought experiments. That's it. Thank you.